Hi, I'm Dr. Kcl Montgomery, and in this video we'll be going through a problem given on previous exams that makes use of an operational amplifier, or an op-amp, in a given circuit, and asks basically the question of what is the output of that op-amp going to be as a function of the input. So here, maybe a little bit different than an arrangement you might have seen otherwise. Here I have a current source that's providing my signal, basically, that's running into the input of my op-amp, and then we see that V0 is indicated as such here on the output of the op-amp. I have a plus minus 5 volt supply to the op-amp. So again, keep in mind that's going to kind of limit the range of the output voltages that I can have. And specifically to kind of start with, again, we always want to pay attention to our various sort of terminals and what's indicated here. So the positive terminal indicated as VP, V sub P, and then the negative as V sub N. And then knowing also that if we're talking about solving this op-amp problem or op-amp circuit under the ideal case of the op-amp specifically, then under the ideal voltage condition that we have, this would indicate that VP needs to be more or less equal to Vn. And so we're going to operate under that assumption, okay, meaning that the voltage here at this point, Vp, must be equal to the voltage at that point, Vn, as it were. Now just kind of make note in this case, because we see that V0 is tied due to this negative feedback loop here with no resistor. Therefore, we know that the voltage Vn must be equal to the voltage Vout. And so that'll be also a very helpful starting point in this particular problem, because now we know that the voltage at this point on the output is equal to the voltage at each of the two inputs, and we can go about getting to a solution. Again, solving for what we're getting to is what is the output voltage V0 as a function of this input current source Is. And then we'll also look at a couple of specific cases based on the values of that current source Is and what the value of Ix, which it should indicate as the current through this branch, and also what is V0 as a function of these two conditions here. So first we'll kind of get right into going through how we solve for V0, and we'll go through that in a minute. Also, just kind of pay attention here. You should always be able to kind of look at an op-amp problem or op-amp circuit such as this and relatively easily identify what type of circuit it is. At least with this one, where we only have one source that's providing a signal, we basically pay attention to what input terminal is that source connected to. In this case, it's connected to the positive terminal, and therefore what we do have is a non-inverting amplifier that I've already indicated here in the heading. If it was the opposite case, if this source was tied to the negative input terminal, then of course this would be a case of an inverting amplifier. And then the other cases of a summing or difference amplifier would be if we have two different sources, one on either side of the input of the op-amp. Okay. So go ahead and take a minute right now, pause the video to at least copy down the problem so you have this in your notes, and then we'll start going from there, working through the solution. Okay, so to get started on this problem, again, we were making first note of the fact that V0 in this case is equal to Vp and Vn. I could indicate V0 as the voltage across, say, this 1 ohm resistor right here. And that will help me because then I can start to relate that output voltage to my input current source here. Now if I indicate this node is at a voltage of, let's say, Va, just for kind of reference sake. Then let's try to relate this V0 with respect to Va. And here we could see that we would have a kind of a voltage divider type of equation, because V0 is the drop across this 1 ohm resistor, whereas the total drop across the 2 ohm and the 1 ohm is Va. Again, we could explain that by using simple KVL type of expression. So here if I wrote that out to say that V0 is going to be, the voltage divider is the 1 ohm resistance over this 1 plus 2 ohm resistance. That'll be 3 times whatever the voltage VA is specifically. So that then tells us that this voltage VA is equal to 3 V0, our output voltage. All right. Now thinking about writing a Kcl equation or expression at this node VA, that will then tie in this current source we see and help us to get, again, a little bit further along with what we need to do. So if we say that the current coming into this node right here would be Is, has to be equal to all of the currents flowing out of that node. Again, sort of thinking back to the way we did things with the node voltage type of analysis, then we could say we have a current out this branch, which would be VA over the 3 ohms that we have there, plus VA over another 3 ohms, because the current traveling out through this branch is going to travel through the 2 ohm resistor and then down this 1 ohm resistor. Again, because this is an ideal op-amp, we assume that the current flowing in to the input terminals is negligible, or basically 0, and so therefore all the current flowing down this branch must go across this branch, so I can simply write, again, VA over 3, which is 2 plus 1 in this case. All right, and then for my final term, which would relate the current traveling out through the upper branch over here, this we could relate by saying VA minus V naught, because at this node right here we have the voltage V naught. That drop is being dropped across the 3 ohm resistor. So again, say VA minus V naught over my 3 ohm resistor. Again, this is 3 ohms on the top branch right up here, okay? So a little simplification, rearranging, we should come up with that IS is equal to 8/3 V naught, all right? Or otherwise, relating then, V naught is equal to 3/8 of IS. And so then, and again, this is, we got to this point here by substituting in what VA equals. So if you take this VA, plug it into this equation, solve. Of course, we have common denominator there, so fairly easy algebra. To get to this point, we'll come up with this expression, then just rearranging this equation, come up with this expression, which is our final one, which then relates our output voltage is equal to 3/8 of whatever the quantity IS is. Now again, pay attention that this is still in units of volts, even though the voltage is, in this case, based on the value or the level, the magnitude of a current source right here in that case, okay? Okay, so now with that information, we can go on looking at these two specific cases. If we have IS equal 8 amps or IS equals 16 amps, how will that affect the current IX that has been indicated here, and how will that affect the voltage V naught specifically? So let me take just a quick minute to erase this, and we'll take a look at those cases. Okay, so in the first case here, if IS is equal to 8 amps, so let's say what is V naught going to be. Okay, so if I plug in 8 to here, we should see that V naught will just be equal to 3 volts, right? Again, this is our general expression relating those two factors. Now, if we want to know specifically, if the question is asking us what is this current IX, well, again, we should note that because we know the voltage drop across this 1 ohm resistor is equal to V naught, therefore we know, again, simply through Ohm's law, this would be V naught over the 1 ohm resistor, which of course V naught we've solved for is 3, so this would just be 3 amps, right? Okay. Okay, now for the second case, if we have IS is equal to 16 amps, right? Okay, so if IS is 16 amps in this case, then plugging this again back into our original equation for what is V naught, this would say that V naught would be equal to 3/8 times 16, which then would give us, what, 6 volts here. Now, in this case, we need to recall what we said at the very beginning of the video, which is the input power supply to our op-amp is plus or minus 5 volts. And again, as we've talked about, we know that the input supply to the op-amp is going to limit the range of the output voltage, because once we surpass that range, we saturate the op-amp specifically, and so we'll saturate it either plus or minus 5 volts. So we see that we've calculated a value of 6 volts here based on an input current source which is set at 16 amps. And so again, that might sound a little bit confusing, but again, the solution that we found here, the general solution, was based on the case that we were operating in the linear mode of operation of the op-amp. But now that we've plugged in a value of IS given in the problem, and we see that, oh, well, in this case, if the current source really was at 16 amps, we would be over that bound, that limits our linear mode of operation, and then we would be saturated, as it were. The op-amp will be saturated in the positive saturation regime, and therefore this will limit always V naught to be whatever the positive value of the VCC quantity is, so plus 5 volts here. So again, even though we calculate the 6 volts, we need to pay attention always to whether or not that falls in the range of our plus or minus VCC that's powering our op-amp specifically. So in this case, we are limited due to the value, and the output would have to hold steady at 5 volts specifically, okay? So again, just to kind of recap here, an important note when we started off this problem was being able to pay attention to, number one, remembering the fact that our two inputs need to be at the same potential using the mode of operation that it's an ideal op-amp and we're in the linear mode of operation. And in this case, we saw that because we had this negative feedback loop, which didn't have any resistor in it, therefore that made the output voltage exactly equal to whatever the input voltage was, and that was also equal to the positive input voltage through the condition that we set forth originally. And so knowing that, that'll enable us to really get started in writing those equations that we had and solving for the general solution here. And then again, as we saw for specific cases, just always paying attention to whatever output voltage you calculate, making sure that falls within the range, the limit of the input power to the op-amp itself, okay? So I hope you enjoyed that video, and I will see you again on the next one.